now let's talk about cars turning on a banked road. And I want to go through what this means since I'm not sure this is something that people normally talk about outside of physics class. The book has this very helpful picture of a race car. And what you have to appreciate is that this is actually the right orientation, that this is up, that the surface of the car, the surface of the road is at an angle as it's going through the turn. So this picture is a little hard to see what's going on, so I wanted to talk about it in some other situations, partially so you also understand that this is a general phenomena. We're usually going to talk about it in terms of cars, but lots of other things do it too. So this picture I really liked in that it is a little toy racetrack. And you can see that the little track is flat through the straight parts. Then it's actually curved, it's banked, it's curved in this very specific way at the ends. So where it's circular, the edge is higher than the inside. And you can see on this far corner the same thing's happening as well. The edge is lifted up. So the idea of a banked turn is that wherever your cars are trying to travel in a circle, the outside edge is higher than the inside edge. So if I dropped a marble here, it would roll towards the center of the circle. So this isn't just something with cars. This happens in other situations too, though I think all of the situations I can think of are at least athletic in one way or another. So the picture on the left is a velodrome, a place for doing inside track bike racing. And again, it's a little hard to tell from the picture, but this way is up. You can see that the track they are racing on has a huge curve to it. And again, that's what's necessary to actually have the cyclists be able to take a turn. And we'll talk a little bit about why that is. So indoor bike racing, the cyclists get really, really fast and the track is turned. Obviously, outside bike racing, that's not necessarily the case. This picture here, some of you might be familiar with this, others might not be. This is roller derby. And roller derby gets played both on a banked track, which this picture shows, and a flat track. So if you've ever gone and seen the Atlanta Roller Girls, they play roller derby on a flat track, which is just easier to create. A banked track, again, it's a circular or an oval track, and you have this raised outer edge, and they're roller skating. So again, every of these situations involves wheels and this raised outer edge on a curve. Roller derby is really fun. I encourage you to learn a little bit about it. There was a movie called Whip It that came out a couple of years ago. And again, just down the road on Ponce, you can see the Atlanta flat track team, who's pretty good. So roller derby, people are roller skating on this banked track. So why do banked tracks exist? Banked roads or banked tracks, banked curves, make it easier for an object to turn. So let's again go through a car turning, but now it's not on a flat road, it's on an incline. And again, it's really good to draw this picture so that now you would actually see that you have an incline, right? So something to be careful about here is to draw your coordinate system correctly. So let's draw our RTZ coordinate. So on this top picture, we have t, our tangential coordinate is forward, our radial component is in, and then our z is out of the page, right? So now let's come down here to this rear view. So r is into the page. Sorry, not into the page, is into the center of the circle. The tangential is forward, so it's into the page, right? And so that's our tangential. So now what about z? And this is a little bit tricky. All three of these coordinates need to be at a 90-degree angle from one another. The z, is not perpendicular to the curb, is not perpendicular to the road. What you need to do is say that z is up. And the reason is that this must be a 90-degree angle. So if you tell me here that z is perpendicular to the road, your coordinate system's wrong. It isn't valid there. So that's one reason why, again, it's really important to make sure you understand what's happening. So now, what are your forces? In this case, we are not going to think about friction. We are going to say that there's no friction, right? Maybe it's really icy. Well, we have a normal force and we have a gravitational force, and that's it. So when I draw my free body diagram, my normal force is at an angle, right? My normal force is not along the z direction. My gravitational force is still straight down. So what happens is that you do have a central force, and we predict there to be a central force based on our model that says if you have an object in uniform circular motion with a constant radius, you know that you have a centripetal acceleration, and if you multiply that by m, you get your net force. So there must be a net force towards the center, and that is actually the radial component of the normal force. So you can use this to say that it is not accelerating in the z direction, it's staying in the same place on the curve, and so your z components of your normal force and your gravitational force cancel out so that you have a net force in the z direction of 0, but your net force in the radial component comes from your radial component of the normal force. So this is a case where the normal force is providing you your central force. So again, be careful here, there's not some additional force making the car go towards the center, and in this case you would have to be told to not worry about friction, or what is necessary to make this work if there was no friction. So here you go, we actually are able to have a car go in a circle, or in part of a circle, just from having the road banked a little bit. So let's go through the final case, which is where we have a banked road, so this angle here, and some friction. What happens then? So the first thing is that we're continuing on from the previous version, where this v naught in both of these represents the correct speed for no friction. And that is assuming a certain radius and actually a certain angle as well. So again, in that previous situation, we could calculate a specific speed that would be the correct speed for the car to take that turn based on the radius and the angle where your forces balance and your normal force just works. Well, what if you go a little bit slower or a little bit faster? If you're going a little too slow, then you actually have less of a net force towards your center. And again, what this is coming from here is that the magnitude of your net force is just equal to your net force in the r direction, which is equal to mass times your centripetal acceleration, which is the same thing as your radial acceleration, which is mv squared over r. So what if your v gets smaller than before? That means your F net is smaller. Same radius, smaller v, smaller F net. Well, nothing has changed about your normal force. Nothing has changed about your gravitational force. So how can your net force be smaller, since you're going in the same circle at a smaller speed? You actually have some friction now between your tires and the road that's preventing you from sliding down. And again, how you can think about this is that if I was trying to go through a banked curve on an icy road, it will work for the right speed. If I went a little bit too fast or a little bit too slow, my car is not going to make the curve. So that's what's going on here. And friction is what kind of picks up the slack. So again, if I'm going too slow, that would be my car sliding down the curve, and friction prevents it. If I go too fast, right, so my net force magnitude is bigger because my speed is bigger, that the way that that will work is that I have a frictional component that is now going down the ramp, providing additional component of the net force, preventing me from sliding up the ramp. So again, I really find these situations interesting where you have both friction and the normal force playing into a central force problem. It's hard to get much of a feeling for. Again, if you've ever driven on an icy road, that's kind of the best way to really gain intuition of it, though it's dangerous, so I might not recommend it. But again, going through and actually drawing out the free body diagrams carefully and identifying your forces carefully will also help. So you can have both friction and a banked curve, and in that case you have more of a play between your speed that you're going, since your F net can now vary based on the amount of static friction you have. But remember, there is a maximum amount of static friction possible. So if you think back to when we learned about friction in chapter 6, the static friction force can vary. That depend if you have an object that is not moving with respect to the surface, and in this case it's sideways with respect to the surface, my frictional force, my static frictional force can vary, but up to a maximum value. And so actually, if I go way too slow or way too fast, such that the frictional component here hits the maximum value, now I slide out of the curve, or now I slide into the curve. So again, there's a lot of forces at play here, and defining your coordinate system very carefully is going to help a lot. So finally, I want to summarize everything we did in this fairly long sequence of videos. First, remember that we're talking about uniform circular motion here. Later on, we'll talk about non-uniform circular motion. So we know these yellow vectors here are our acceleration. And we already said that we have acceleration towards the center of the circle, centripetal acceleration. This is back from chapter 4. Now, based on Newton's second law, we know that these red or pinkish vectors are the forces, that we must have a net force towards the circle. So now this is saying a force component, because if you have non-uniform circular motion, you have a force component, not a total net force. If it is uniform circular motion, your entire force is towards the center. And what's really important is you are always using that RTZ coordinate system to analyze these problems. So some bullet points again: use and show your RTZ coordinate system. The book uses the radial direction, the radial unit vector, towards the center of the circle, but many other situations and what you might be used to in polar or cylindrical coordinates would point that away from the center. Physics will still work. You can still do your problem if you define your radial component away from the center, but you must show me what coordinate system you're using, since otherwise I'm just not going to know how you're defining things. We can relate our centripetal acceleration to the net force in the radial direction. And again, this is going to be for uniform circular motion. That's the entirety of your net force. For non-uniform circular motion, it will be a component. So in the tangential direction, or the perpendicular z direction, our net force is 0 for uniform circular motion. So again, identify from the information that you have in the problem whether or not uniform circular motion is the right model. The other model that we talked about in the video here was that idea of the central force model, which allows you to basically do this for a fixed radius. Lastly, remember that when you have circular motion, it might even be components of the normal and frictional forces that are providing the net force. And the reason for that is, again, thinking about these objects traveling on curves. Tension is going to be another one that comes up, but there's not some additional magical force towards the center. It's always going to simply be the net force that is arising from summing up all of the other forces that you could identify normally.